So let me take for a second.
Sure.
My name is Vladimir Svetnik, and I'm distinguished scientist at Merck. And there is a good tradition that Merck and NISS are organizing meetup or webinars on different topics, which are very important for practicing statisticians. And today's webinar would be on conformal inference, advancing the boundaries of machine learning. With this, I hand over to Yuting, who is the moderator of this seminar.
Hello, everyone. My name is Yuting, and I will be the moderator for today's event. We are fortunate to have 4 distinguished speakers today. Each of them will give a 25 minutes presentation followed by a 5 minutes Q&A. If you have any questions, please submit in the chat anytime, because if you miss the 5 minutes Q&A after the talk, there will be a second chance to ask questions for all speakers at the end. Our first speaker today is Professor Alexandra Donovan from Royal Holloway University of London. Professor Donovan has published about 200 research papers and several books on computational learning and probabilistic inference, including the very famous book about conformal prediction, the algorithmic learning in a random world. The title of his presentation today is Conformal Prediction and Testing for Change Point Detection. Professor Donovan, we are all very excited to hear what you taught. Please go ahead and get started whenever you are ready.
Okay, can you hear me now?
Yes. Could you share your screen?
Yeah, just 1 second. I will share the screen if I can. Is it okay now?
Yes, wonderful. Please go
Great. Okay. Thank you very much, Vladimir, for your invitation, and thank you National Institute of Statistical Sciences for setting this up. My talk is today about conformal prediction and testing, and in particular for application and change point detection. Let me move a little bit this. My plan is quite simple one. I would like, after a short introduction, to talk about conformal prediction as such, just to remind you what the main ideas, because also it has a sort of background for conformal testing. And then on conformal testing, I will talk about type of martingales called conformal one, and show you some experimental results also using different procedures for change point detection, called Willi procedure, cumulative sum, and Shiryaev-Roberts. And a few words in the conclusion of this. You can interrupt me at any point if you want to ask something. Historically, these ideas of change point detection was motivated in problems in 1920s, 1930s, when people started to talk about quality of quality control in manufacturing and other places. When a process in control, the observations usually follow one distribution. But sometimes, and quite often actually, in unknown time point tau, the process may go out of the control, and subsequent distribution changed. So in principle, we would like to raise an alarm as soon as possible after the process jumps out of control. And also, of course, for this in control, people apply certain machine learning algorithms, or just different algorithms, statistical one. But of course, it's important if if a distribution has changed, the algorithm has to be retrained. And that's what this talk is all about. So the problem is to find some detection in change of a distribution. And of course, a lot of majority, well, really majority of machine learning algorithms developed under so-called IID assumption. IID stands for data are independent and identically distributed, or sometimes a slightly weaker assumption than IID called exchangeability. Basically, exchangeability means that examples can be exchangeable if it's invariant to with respect to any permutation of examples. But it's quite popular testing the IID in statistics. It has been for quite a while, but most of the work has been actually from so-called batch setting. But it's of course much more important to deal with the online setting, because we want to have an idea at what particular time the distribution has changed, and that's only online setting allows us to do this. Also, in many works in statistics, each observation is a real number. But in machine learning, we usually would like to deal with a pair X and Y, meaning that X is a vector of attributes and Y is a just label. So instead of just real numbers, have a pair of them. There are some classical methods of change point detection. Wille, cumulative sum, Shiryaev-Roberts. I would talk about them a bit later. But there are some quite a strong limitations of these classical methods. They all require prior knowledge of distribution before and after the change. And that's what we would like to escape, because not always we know what's the distribution before and after the change point. So our approach is to use conformal predictors. No need of information about distribution, and they allow this conformal predictors allow us to construct a martingale to test this IID assumption. Okay, so a little bit about conformal predictors. This is a modern machine learning technique, as I said in my slides. Perhaps the most important property of this is its proven validity. Validity here means that the true label of a new example will be included in prediction region with a guaranteed pre-selected probability. What does it mean? It means that if you want to have certain confidence in your prediction, let's say you want to have 95% confidence in your prediction, we can guarantee that you will not make more than 5 errors out of 100. And that sort of validity means in conformal prediction setting. More accurately, if we are given a set of sequence of observations Z1 to Zn minus 1, and each Z is a pair, X and Y, X vector of attributes, Y usually label of that. And then new observation arrives, Xn. And our task is to estimate Yn. It can be done in classification, it can be done in regression, and that's how the idea of conformal predictors works. You are given this a set of observations, let's say training set, from 1 to n minus 1 observations. And a new example arrives, and you would like to know how well this new example fits into the training set or conforms, because we assume that the training set following IID assumption. So how well this new example conforms with IID assumption. That's the main idea of conformal predictors. So in order to do that, we set up a number, a function which we called non-conformity measure. We would like to know how different, how strange, how untypical a new example in comparison with a training set. This non-conformity measure here, or alpha we call it, and here is some definition. It's a function that assigns to every point a number alpha called non-conformity measure, such that interchange of any two examples leads to interchange of corresponding non-conformity scores. Okay, well, that's okay for non-conformity measure or how strange each example is. But in itself, it's not enough because we need to compare this alpha with other non-conformity scores with other observations. And that's how we compute a function called p-value, usual statistical p-values, when we have got in this setting, we counted how many alphas is greater than the new example alpha, greater or equal actually. So we set up this p-value, and p-value allows us to compare our new example and how well this p-value is. Of course, when small non-conformity measure means that the example is non-conforming, and then the larger one, of course, tells us that it's conforming. P-value itself is, as you can see from this formula, can be defined in interval between 1/n to 1. When so from that point of view, the higher p-value, the more suitable, more typical of new example is. And of course, as our set of different PhD students and the rest developed from different machine learning algorithms, you can extract non-conformity measure and corresponding p-values. For example, if you deal with support vector machine, if you remember, it's when each support vector is Lagrangian. So our alphas can be Lagrangians for support vector machine. For neural networks or for nearest neighbors or others, it can be developed and extracted. And another interesting point here is that we can end up our prediction by assessing how confident we are in each observation, predicted observation. But sometimes it's more important, more useful, or impossible to do this, and we can't really predict one particular observation, and we end up in prediction set, which is which includes all possible labels given certain confidence we require. As you can see from this formula, we find label yn when our p-value is greater or equal than epsilon. Epsilon here is significance level. So once we set up significance level or 1 minus significance level confidence level, we may end up with a so-called prediction set where all different labels are given. Okay. Well, here is a summary of this. Given the strain set and new example of a test set, and we also set up what confidence we would like our prediction to make or significance level, and ended up in prediction region where yn is predicted label of xn, new example. And this probability that this new label belongs to our set of labels should be greater or equal than confidence level 1 minus epsilon. Quality of confidence predictor has two parameters, two properties. I mentioned before validity. That is perhaps the most important property. The region contains a true label with probability at least 1 minus epsilon. And effectiveness this we would like in principle to have our prediction set as narrow as possible, preferably just a single label, but of course not always possible to do this. Okay, here is a well-known set of handwritten digits taken from United States postal data. And as you can see from this slide, we can, in online setting, make certain calculations. Here are the examples of this USPS data, slightly more than 9,000 of them in online settings. This is online. So each example come at a time and we make sort of prediction and other things. And on Y coordinate, we put cumulative errors, multiple and empty predictions. I will explain in a second what they are. But let's concentrate first for cumulative errors. As you can see from this slide, we requested the confidence level 97.5%, meaning that we have 2.5% of our significance level. And therefore, we should not make more than 2.5% of errors after 9 with something thousand examples. And indeed, up to a fluctuation, it is a less, about 225, maybe slightly more or less. There are two other curves here. One is this curve is so-called multiple prediction. It's our prediction set, when we can't make more than just one particular label or just several labels. And if all depends upon what sort of confidence we require. And of course, sometimes it's not possible to find any prediction, and we call it empty prediction. Similarly, with this so-called NISS, also handwritten digits from National Institute of Statistics in America. And you can see there is a number of different curves showing how the in online setting, 5%, for example, of this NISS has about 70,000 and 10,000, 60,000 for training and 10,000 for test. And 5% should not be more than 500 errors, which it is, or 450, sorry. Okay, let's now talk one more important point, perhaps. We need to to express, or sometimes we can express, p-value generated by conformal predictors are independent and uniformly distributed in the interval 0-1. That's sort of it's been proven, of course, and it is important property because we are going to use it for conformal testing. And property allows to test IID by calculating martingales as a function of p-values. Okay, so let's move to the conformal testing. We would like to now to construct a martingale, and actually this idea came to in 2003 in our paper in ICML conference, and then in our book in 2005. And actually, I forgot to mention that all I'm going to talk, I have been talking and will be talking. It's been in our second edition of our book. So if anyone wants to or miss something, you can look at the book, of course. Anyway, martingale is, of course, a sequence of random variables, and this equations 2 tells us a definition. Martingale is a sequence of random variables for which at a particular time, and here is the main thing, the conditional expectation of next value is equal to the present value, regardless of all prior values. The validity of this is expressed by so-called Willi or Doob inequality, when probability of certain martingale greater or equal than constant C should not be more than 1 over C. For example, if you set up your constant C as a threshold of 100, so probability of that martingale will be greater than that, will be no more than 1%, 1 over 100. Oops. So martingales, we use martingales in by taking p-values. P-values are independent and, of course, identically distributed, and we can use them as a set for finding martingales. Actually, there are two steps. The first step is to generate p-values, as we do it in conformal predictor set, and second set is to construct a martingale. Martingale, of course, all different martingales are related to their betting functions. And here is, for example, so-called power function, betting function. And sometimes we take the mixture of power function and take an integral of this.
We have 5 minutes left.
Thank you. Thank you. So this USPS data, you can see that when the data are randomly permuted, the martingale doesn't rise. But if you take an original order from US UCI data set, it will rise. Okay. I skip this one. So the property of validity, as I mentioned, follows so-called Willi inequality. And here is a sorry. Here is a data we experimented with. We took the wine quality data from UCI repository, and the label. The idea, the problem is predicting the label. And this data has about 11 different attributes: sugar, alcohol, and so on. And we train on there is about 5,000 white wines and over 1,500 red wines. We take training set only white wines, and then 2 test sets. One is just also white wines, and another is red wines. And then we consider 2 scenarios when we train on a white wines full training set and test on them called test on 0. And similarly, we train on the white wines, but test set 1 is just red wines. We change from white to red. And here is accuracies of various prediction algorithms. You can see the different algorithm we tried of random forest, nearest neighbors, multi-layer perceptron, support vector regression, checking every time mean absolute deviation. And of course, zero scenario when we train on the white wines and apply to white wines is much better than, of course, than when we train on one and apply to another. Similarly, that's how this works. And by making also from white wines free folds, we applied them free folds on this, and you can see that to begin with, up to a certain point, when we have got training and calibration and test set, when we don't have, we train on white wines and apply to white wines, martingale is still the same. But when we apply to the red wines, martingale started to raise. We use here also, the multi-layer perceptron similarly, and support vector machine regression on the right side. Anyway, maybe the most important point here, procedure tells us when to retrain. We may decide to retrain when one of the three martingales exceeds threshold of 100. And then the probability of ever rising false alarm never exceeds 3%. Anyway, there are some disadvantages of Wiley procedure. So people applied also so-called Shariaev-Roberts procedure, and here are their results. In all cases, we can find some point when the detection distribution changed. And here are all three of them, all three different procedures, different conformity measures, different algorithms, and delay, mid-median delay, and interquartile intervals. The best one is nearest distance 29. So in conclusion, conformal prediction for testing IID is only known way of constructing non-trivial conformal test martingales. And there is also a proposed procedure that combines advantages of classical scheme, but I haven't talked about this now. This work has been done in collaboration with Vladimir Vovk, Ilya Nuredinov, and Ivan Petesh. And here is my set of references. Thank you very much.
Thank you, Professor Zimmerman, for the wonderful talk. I truly hope we have more time to finish all the later half of your presentation. I would want to include this material in your in the new version of your book, the second version of Algorithmic Learning Around the World.
Shall I stop sharing then?
Yeah, sure. Well, I don't see any specific question in Q&A. So let's thank Professor Donovan again and move on to our second speaker. The second speaker today is Professor Yao Xie from Georgia Institute of Technology. Dr. Xie's research lies at the intersection of statistics, machine learning, and optimization in providing theoretical guarantees and developing computationally efficient and statistically powerful methods for problems motivated by real-world applications. The title of her talk is Sequential Conformal Prediction for Time Series. Now I would like to hand over to Professor Xie to start her presentation. Yes.
Let me unmute myself. Yes. Hi. Thank Dr. Xu for the very kind introduction. And it's my great pleasure to be able to talk here. And I also want to say thank you, Dr. Gummerman, for the change point conformal talk. Change point is one of my favorite topics. But today I'm going to talk about a different one, which is time series. So this is a joint work with my PhD student, Chen Xu. And the plan for today is so first talking about the motivations, and then I'll introduce the setup and present two algorithms, and then show some examples and also performance guarantees. So we would like to study solar time series data, in particular prediction for time series data And so such application is very widely available. For example, solar energy prediction, where we're interested in predicting how much solar energy can be generated at any given time, different locations, wind power predictions, predicting how much wind power can be generated at different locations in the wind farm, supply chain demand forecasting, and ICU sequential data prediction. Like we're interested in predicting the risk of the patient developing such as sepsis, a dangerous condition. So all of these 4 examples are applications I have worked on where there's a lot of data and the need is to provide an accurate prediction, but also a good prediction interval, not just telling about how much it should be, but also tell us how much uncertainty, what is the range of the possible values. Okay, so this is the setup, right? So suppose we are given an algorithm, FT, and this can depend on time. A lot of times it's pre-trained, so it doesn't depend on time. And given a sequence of observations, so it's time series, so the observations arrive one at a time, for example, in a sequential fashion. And we would like to come up with a prediction for the next step or next few steps. It can be one step ahead or a few steps ahead. And so we would like to provide a point predictor, but also give a confidence interval. And so why it is important? So I find this example particularly interesting. This is an article published in NPJ Digital Medicine, a journal of Nature, basically says artificial intelligence algorithms, AI machine learning algorithms to be really useful, then they have to not only tell us what number it should be, but also tell us how uncertain it is. If the uncertainty interval is huge, for example, that's an indication of saying they don't really know what the answer should be. Okay, so we really need to provide such an uncertainty quantification. And so then we talk about in traditional time series how this is being done. For example, a RAMA model, autoregressive moving average model, which is basically based on assumption that the past predict the future in a linear fashion, and the prediction intervals can be derived analytically based on the distributional assumption, typically Gaussian, such as this example here. And however, nowadays, right, a lot of the algorithms, popular algorithms used for time series prediction are black box machine learning algorithms, such as RNN, LSTM, and it has good performance in making prediction for complex real data, because probably it explains the high nonlinearity, non-stationarity, and so on. But coming up with a prediction interval, especially with performance guarantee, is still an open question, right? It's a black box. It's very difficult to explain what's exactly happening inside. So the goal here is, can we come up with a prediction interval algorithm based on maybe conformal prediction for general machine learning algorithm that also has a guarantee? And so the challenge for doing this is the real world time series data can be non-stationary, and in particular, data is not exchangeable, which violates one of the basic assumptions made in conformal prediction analysis. And the time series can also be temporally correlated. And I give some examples, right? This is the solar and power, and where the time series is highly non-stationary and varies over time because it correlates with weather, right? So when the wind blowing direction is changing all the time, and then it's caused a lot of non-stationarity. So here's the setup of the problem that we call the sequential conformal prediction. And suppose we have a sequence of observations, this YT, and the predictors at XT. And there's some true model we don't know, which is this FT. It can possibly depend on time. With an error, suppose additive. This model is for simplicity, but we can extend this to be non-additive noise. The noise following some distribution, which is unknown, and this is why conformal prediction can be useful. And these epsilon t's errors can also have dependence. And so I want to emphasize that these predictors do not need to be just extraneous, but also can depend on the past. So then we can have a general model where captures some kind of nonlinear autoregressive pattern, but also depend on some other external factors. So our goal is to similar to conformal prediction is to find a confidence interval we call prediction interval. We can provide such guarantee in saying the prediction for the next time periods is likely to within this interval with certain 1 minus alpha. And so in particular, we're going to focus on marginal coverage guarantee, we also have results for the more challenging conditional guarantee results. So here's an explanation, roughly speaking, I think what's really happening for sequential conformal inference, which is different from the traditional non-sequential offline version of the conformal prediction. So when we do the prediction sequentially for time series, basically every time we make a prediction for the next period, either tomorrow or next month, next hour, then once we wait a little bit, then we can see the error itself. Right? So we can see how good our algorithm is. So basically, these errors tells us how good the algorithm is, and also tells us how much intrinsic variability there are in the time series. And so the errors where the residuals accumulate over time, okay? And so although the data are not exchangeable, in this case, time series, you cannot shuffle the order, the distribution will be different. We have to preserve the order. But we do have accumulation of these residuals that can tell us information and then help us to build prediction intervals in a real-time fashion. So that's the basis here. And in particular here, we consider the residuals being the difference or prediction accuracy of the observed observation from the past prediction. But this can be generalized to other conformity scores. And so we can imagine the situation is we have observed a sequence of such residuals, and then we would like to make prediction of the, where the next residual is likely to be. And this is based on this work, which is an ICML paper, 2021. And so you can see the setup is different from the traditional conformal inference, where a lot of times the analysis is based on exchangeability. Basically means that you shuffle the order of the residuals, it has the same distribution. But here, we observe one residual at a time, and such residual accumulate over time. And we can use the past residual to predict something about the next one. And that can tell us a prediction interval. And so what does these residuals look like? Here, I want to give a real data example. And so we take this data for solar power generation in Atlanta, Georgia, where I live. And then we use a random forest to perform one step ahead prediction, predicting the solar power generation in the next hour. And this is a histogram. You can see the residuals I skewed, this indicating that the algorithm can be biased. And if you look at the temporal correlation residuals, it has a temporal correlation. Okay, so basically when we use these residuals to provide a confidence interval, we want to take into account these two characteristics. And so it's easy to write down what the residual really consists of. As you can see, if this is our observation and this is our prediction, right? The difference between the two is going to be, you can group the first term, which is basically, this is the true model, and this is our estimated model from the algorithm. And this difference is basically caused by the algorithm itself. Of course, it depends on the predictors itself, but this is basically depending on the choice, how good the algorithm is. And there's also the nature introduced the randomness or stochasticity. So basically, if we look at the histogram or empirical distribution of these residuals, it tells us both how good the algorithm is and also intrinsic variability. And that's our idea of building such prediction intervals. We'll present two algorithms. The first one is which is called the ENBPI, which is basically based on empirical distribution of such residuals. And we can provide some guarantees for simplistic case IID, but also weakly dependent and alpha mixing. Here, we're not going to consider exchangeability because usually time series is not exchangeable. And in the second improved version, we further consider how to capture the temporal dependence based on quantile regression. And we can also provide performance guarantee. And this is illustrating what this roughly look like for the two algorithms. The top one is based on empirical distribution. And then the bottom one is spicy. Basically, this is based on quantile regression of the past residuals. And so we observe that both of them can achieve pretty good coverage guarantee. And then the second approach based on quantile regression that take into account the temporal dependence can further reduce the coverage width. We can have a narrow confidence interval still with the same coverage probability. And now let me explain how are these algorithms constructed. So first, I want to quickly go through some of the previous work, and it's a huge literature, so I probably will not be very comprehensive, but I would say roughly speaking, in the traditional classic setting, such as the original work by Wolf and our speaker here, and basically considers the split conformal. And recently there are also being jackknife approach and conformalized quantile regression. And so those are designed for the setting where we can shuffle the data. And so what goes wrong if the data is not exchangeable is if you look at the guarantee proof, then one of the key steps, which is based on the shuffling invariant distribution of the conformity score, doesn't carry through anymore. And so we start thinking about this and think, okay, maybe we don't have exchangeability, but in time series, there's something else we can use. And so what is something in time series analysis that we can use to replace exchangeability? And it turns out stationarity and strongly mixing are the assumptions we can use to still provide guarantees. And so recently, there are also been a lot of interest in going beyond exchangeability because in real world data, sometimes the data is not really exchangeable. So a lot of them are based on studying distributional shift. For example, there are algorithms provided saying we should reweight the conformity scores when we construct the prediction intervals, or based on adjusting the alphas, which is the target coverage probability based on observation of the past, how good the coverage is. So these are all recent works. And so they can be potentially applicable for time series data. But I would like to say that this is still, I think, pretty open question, like what is an optimal algorithm that can be applied for non-exchangeable and time series data. I'm going to compare with this algorithm as well. Okay, so this is our first algorithm, which is quite intuitive. Basically, it says we can use the most recent observed residuals, and then let's just look at the confidence interval of that. And so FT hat is a given algorithm. You specify this. For example, this is your LSTM, this is your recursive neural network, recurrent neural networks, or this is your random forest, any complicated algorithm you want, or maybe a simple algorithm. And then you look at the residuals happened in the past sliding window from T-1 to T-W. The choice of this W is also important because this reflects in how much residuals you want to use to build your confidence interval and how much you believe that you can trust the past residuals. If you believe the past W period residuals are more or less similar, then we can choose the W accordingly, right? This cannot be chosen to be too long. Otherwise, what if the residuals distributions have shifted drastically? So this is the choice tuning parameter. And so we can provide a performance guarantee for this. And we can also extend this to be a practical algorithm based on ensemble learning. So basically, the idea is since, in time series prediction, let me just go back a little bit, that we are observing one residual at a time. And then this is something we want to predict based on the past residuals. And so in order to make the algorithm more accurate, we can generate some bootstrapped versions of the prediction residuals. So that's the algorithm here, right? We can combine this approach with bootstrap, bootstrap. For each bootstrap sample, we can fit one predictor, and then we build an ensemble of that can help us to get more kind of past residuals to improve our prediction accuracy, and also better prediction coverage guarantees. And so this is one comparison of this proposed approach with standard method, as has been advertised, that the traditional parametric time series model, ARIMA, it does have the coverage, prediction interval, which is specified analytically. However, as you can see here, that for real data, it's not performing very well because if we specify alpha to be 0.05, the target coverage should be 95%. Using the EMBPI approach based on conformal prediction, we can achieve this pretty accurately, but ARIMA is significantly undercovering. And you can see here as well, and here as well, right? And so that is one problem with such parametric model when there's model mismatch. And we also compare with other approach, which I'm going to present more results later as well. But I just want to move into the next topic, which is how do we further improve this? EMBPI seems to be very intuitive, using the past residuals and look at the empirical distribution of that to construct a confidence interval centered around the predictor itself. But one thing probably we haven't been using is that such residuals may have memory, since remember, this captures the fact that the algorithm itself may be biased, but also the nature-generated stochasticity in the time series, which can have memory. So if we just use this, then we are ignoring this kind of memory in the time series. So we thought about to improve that, and we can potentially, a lot of times such residuals, possibly if you're doing a good job extracting such from the time series, the sequence of residual form a stationary process. That means that if we take a chunk of W sequence of residuals and we shift it by a certain unit time, the distribution doesn't change. Based on this, that means we can construct quantile regression, means that we can use the past residuals to predict the quantiles of the next residuals and use this together with a point predictor to come up with a prediction interval. And this is the so-called spicy algorithm. And so this can be coupled with any quantile regression. And so also we can establish guarantees by combining our analysis for conformal time series together with the quantile regression guarantees. And this does give us better performance. So I'll skip this. Basic quantile regression is a type of regression methods where you choose this kind of loss function to call the check function, and then you can also add additional regularizer to it. Okay, this could be an interesting comparison here. We basically look at 3 data sets: the wind prediction, electric. This is the electric data, tracks the electric usage and pricing in the state of New South Wales in Australia. And the last one is the solar power. And so we look at the coverage guarantee together with the width of the confidence interval for spicy, the second approach, EMBPI, our first approach, together with 2 state-of-art methods that can be applied for time series. And you can see our algorithms has reasonable coverage, but spicy and EMBPI has much smaller, especially this one, spicy, has much smaller width, achieving the same precise guarantee. Okay. And so it also has, this result basically is averaged over the entire time period. But if you look at the instantaneous coverage, the spicy and EMBPI also have pretty good performance for these real data. And this is the burning period. So basically says, suppose we're just starting to run these algorithms, we haven't seen a lot of residuals. How does it perform? And so we compared EMBPI, spicy, and 2 other state-of-art methods. So it looks like these 2 methods are stable, especially EMBPI is more stable, and adaptive is slightly more variance, but it does have smaller coverage width. Okay, last part is going to be about theoretical guarantees. What can we say about this? And so basically, like we said, recall that our method is based on observed residuals. And if you look at what this contains, it captures 2 parts. One is the prediction error or by intrinsic biasness of the choice of the prediction algorithm, and also the nature, right? How much is that intrinsic stochasticity is in the time series. And so basically we can, if we under these 2 assumptions, one is if the error process itself, if nature has a reasonable noise process, doesn't need to be IID, but if it's stationary or strongly mixing, and excuse me, and the true CDF satisfies some technical conditions, and or it is strongly mixing, then we can say something about the coverage guarantee. And the second assumption is that we need to have a reasonable prediction algorithm. This means that the average prediction accuracy can be bounded by some constant. And so if under such 2 conditions, we can achieve such coverage gap upper bounds, which is on the order of log t. And so this basically says how this decays as the horizon, okay? As we observe more and more residuals, we can get a better performance. And so you can see it consists of these 2 factors. This factor comes from how good the algorithm is. If the algorithm is fairly accurate and captures the underlying F, then this term can be small. And the other one captures how much residual we have seen so far. And this order coming from assuming alpha mixing errors. And for different assumption of the intrinsic noise process, we can have different rates. If they're independent, we have this rate. If it's a stationary linear process, we have such rate. And then what's just presented is the strongly mixing rate. And what is a good prediction algorithm? And so there are many good prediction algorithms. For example, if you use neural networks or high dimensional linear models and so on.
Professor, you have 5 minutes left.
Okay, thank you for your reminder. Excuse me. So lastly, I want to say that this algorithm, we can provide guarantee, but it also even works for cases that we haven't proved yet. Okay, so for example, it can handle non-stationary time series and heteroscedastic time series. And we have some simulation example basically to handle non-stationary time series. Means that if the model itself is time varying, then we can modify our FT to include the time information. For example, a lot of times the time series can have a trend, it goes with time or periodicity. And if this F, the choice of our model can capture that, then this can be applied. And the heteroscedasticity basically says if the noise itself has a varying noise, then we can also modify our approach to capture that. And here's some examples to showcase the algorithm still works. And finally, just want to mention that so far I have talked about prediction. Basically, you come up with a number, right? You say that I want to predict a range of possible values for the next observations. But this can also be generalized to prediction set if the observations or the outcome or response is going to be categorical, for example, classification problems. And so we call that the ensemble regularized adaptive prediction set, which can be found in this link here if you're interested. All right, so this is my last summary slide. So basically presented, I think this approach of using conformity scores or conformal prediction for time series prediction, especially handling the aspect the time series is not exchangeable, can be temporally dependent and non-stationary. We present two algorithms, the MBPI, which is based on empirical residuals, and SPICE exploiting temporal dependence to further improve the performance. Both algorithms can have reasonable guarantees. And EMBPIs, I didn't mention the proof, but basically we want to show the convergence rate of the empirical residual distributions from the true population distribution. And so SPICE can be proved further by combining that analysis with performance guarantee for quantile regression. And ongoing work is we find from this analysis that SPICE seems to, it might be solving an interesting problem that has been considered in the series of work of going beyond exchangeability, is that it has been realized that when the data is not exchangeable, then it's probably better to perform a weighting of the residuals or conformity scores. And there's an open question of how to find optimal weights. So we find there could be a potential connection with distribution robust optimization in formulating this problem. And finally, just want to mention that the algorithm has been implemented into several packages, including the freely available scikit-learn, maybe. Then this one has an array of different conformal prediction algorithms you can try out, and by Amazon and also by Meta. If you're interested, here's the reference to the papers presented, and thank NSF for support. Thanks everyone for your attention, your time. Thank you.
Thank you, Professor Xie, for the wonderful talk and very interesting topic. I believe there are a lot of very important applications of time series.
There are two questions in the Q&A.
Yes.
Eugene, right? Do we have a minute or two?
Yes, we have time to ask the questions.
So for the first question is, do we have exchangeability of epsilon if it is IID white noise? It is a standard assumption in a RIMA model.
That's right, yes. So
then we can use the standard split conformal inference method. Is it true?
Yes, that is correct. If the epsilon is IID, then it is exchangeable. And so this analysis holds. In fact, in our paper, we also presented that when you have IID epsilons, the rate can be even faster than the dependence. And then split conformal inference, the difference from here is, I think the setup is different. In split conformal, you basically split your data into training, testing, and then the testing part gets the conformity scores, and you construct a confidence interval on the third part. And so our setting is the residuals can be observed one at a time. You accumulate residuals gradually. And this is a naturally assumed setting for our particular problem for time series. So I guess in the offline conformal, your data has been collected. You will not observe more data, but this is a different setting. I think probably more natural for time series prediction. That's why I have one slide actually comparing split conformal with time series, or called the sequential conformal. I think the setting is different. Yeah, but of course you can still use split conformal, but it's probably not utilizing the structure of the problem. And Yeah, thank you. That's my first answer. And
There is a second question. Do you see them, by the way?
yes, I
Okay.
can. Yes, if you're fine, I can just yes.
Please read them. Read them.
Yes,
and answer.
sure. Yeah, the second one is, I have a question. How do you choose or fix gamma in ACI in your numeric algorithm? Sorry, what is the question about? The gamma is are you talking about the alphas? Which is the target coverage. This alpha is usually pre-specified, if I understand correctly. For example, you want to say 95% confidence interval, then this alpha is going to be 0.05. And do I have a gamma here? I don't remember. I hope that answered the question. So this alpha is usually user pre-specified.
I don't know what ACI stands for.
I don't know what is ACI.
It's asking about adapt CI.
Adaptive conformal interval, right?
That's adaptive CI. I think it's someone else's algorithm. That's by Gibbs and Candice. And basically, they want to adjust the target alpha by past observation because you can overcover or undercover. They use some kind of stochastic gradient descent to update the target alpha as a tuning parameter of the algorithm. That is not our algorithm. It is something we compared with. Yeah. So the next question is, how do these conformal conformal prediction interval look like when the labels can only take two values? That's an excellent question. That's exactly what this conformity prediction sets that we're proposing. Basically, if it is going to be categorical, then instead of having an interval, we're going to have a prediction set. I think being mentioned by the first talk as well. You're going to talk about those set of labels are the most likely ones, something like that.
Thank you.
Yeah, great.
Okay. There's a follow-up question to the previous one. So ACI stands for adaptive conformal inference.
Yes, that's right.
That's gamma from the
Yes, thank you.
Okay, great. Yeah, thank you. Yes, we do have a fixed step size. Well, I have to say we have a fixed alpha. We don't adjust the step size. So it's a different philosophy, different approach, I think. As far as I see or understand about literature, currently two approaches for dealing with non-exchangeability. One is by Gibbs and Candice. They have the static CI, they adjust the target alpha. And so based on the past observation, you see, oh, this is overcovering or undercovering. Then you can adjust your target alpha to enforce your algorithm to match the desired rate, and alpha becomes a tuning parameter, and it's done by SGD, I think online algorithm. And our philosophy is different. We take the approach of essentially weighting the data. So that's actually the analysis we've done when we examine the spicy algorithm. Is that essentially we have the past residuals, and then we use the empirical distribution, but the empirical distribution is a weighted empirical distribution. You have the support, but the weights on these residuals are going to be learned and optimized. And that is done through the quantile regression implicitly. And so that is also something observed in the recent work by Rita Barber et al., which quite nicely captures when the data is not exchangeable, and then you're going to have a performance loss. And then the amount of performance loss can be reduced by if you apply weightings on the residuals. So I think we're taking this weighting approach instead of adjusting alphas. And so I think both algorithms have certain merits. And so in our place, we show some benefits. Okay.
Yeah. Thank you, Professor Xie, for the very detailed answers. It's very helpful. And thank you
problem.
For all the interesting questions from the audience. Let's thank Professor Xie again for the wonderful talk and move on to our next speaker, Professor Matteo Socia from University of Southern California. Professor Socia's research is focused on developing data science methods, combining the power of machine learning algorithms with the reliability of rigorous statistical guarantees. Today, he will present conformal inference is almost free for neural networks trained with early stopping. Now let's welcome Professor Socia to begin the presentation. Yes, we can see your screen.
Yes, thank you. Can you see my screen?
Yes.
Okay, great. Thank you, Vladimir, for inviting me. So today I want to talk about this recent work that was conducted with my two PhD students, Ziyi Liang and Yanfei Zhou at USC. So I'm very grateful for the introduction I had from Professor Gammerman and Xie to the topic. So these ideas should sound quite familiar. So the type of problem that I'm interested in is how to estimate uncertainty for predictions computed by machine learning models. And in particular, I'm going to talk about deep learning models today, even though many of the ideas would also translate to other types of models. You can think of deep learning models for different applications. So today I will talk mostly about classification and regression, but these type of ideas could also be relevant, for example, in testing. An application is a little bit more similar to what Professor Gammerman talked about. So the goal of conformal inference is to estimate the uncertainty of these predictions. And the idea is that instead of making assumptions about the data generating process or about how the machine learning algorithm works on the inside, conformal prediction uses the exchangeability of the data. And by observing how the predictions performed on a holdout data set, one can predict how they will perform at test time. And in particular, uncertainty estimation is obtained with conformal inference by constructing prediction sets in this context that I will be talking about. So if you think about an image classification problem, you observe an image like this image here on the left, you fit, and you apply a deep neural network that was trained on some training data. And instead of just predicting one label, you predict a set of possible labels. Now, in this case, you might feel confident and predict a set that contains only the label ship. And conformal inference allows you to quantify how confident you feel about this prediction. For example, one may say that you were 90% confidence that this is an image of a ship. And uncertainty estimation is particularly useful in situations where we don't feel that confident. And if you have an image like the one shown here on the bottom left corner that is basically masked, most of it is not visible, then we cannot predict very confidently what it is. And this is an example taken from a data set with 10 possible labels. And so just because there are only 10 possible labels and we kind of can rule out that this image is not a ship based on the little bit of background that we see, we might end up with a 90% confidence interval, confidence set that contains the labels dog, cat, and deer, just because these were the three animals that were in the data set. So what property do these conformal prediction sets satisfy precisely? They satisfy this marginal coverage. So marginal coverage means that the probability that the true label of the test point is contained in the prediction set is larger than 1 minus alpha, where alpha is some desired significance level. And this can be achieved by assuming only that the data are exchangeable. Now, the tricky part is that this probability is taken with respect to a lot of different random variables. There's the test point itself, which has features X and label Y. So both of those are random. And then there's also the randomness in the algorithm that is used to construct these prediction sets, which will depend on some holdout data. And those data are also treated as random. Now, why do I say that this is tricky? It's tricky because it's not really the way that we would like to measure uncertainty. The way that we would like to measure uncertainty is at least by conditioning this probability on the features of the observed image. Unfortunately, this is difficult to obtain in practice, and marginal coverage is a useful compromise that is often necessary, but we should keep in mind that there's some subtlety in marginal coverage. And here's what I mean by it. In the previous example, we had two images. One was easy to classify and one was hard to classify. And we said that ideally we would like to see prediction sets that are as specific as possible. So in the case of the easy image, it should be small, it should only contain the right label. And in the case of the difficult image, well, it should be sufficiently large that we're still confident that the right label is in that set for that particular image. And this is what good prediction intervals that also happen to have conditional coverage in this toy example would look like. Unfortunately, marginal coverage doesn't imply that we're going to get with this kind of output. Marginal coverage simply means that you have the right coverage spread out over all possible test points. And one way to achieve that in this two example would be by being overly conservative for the easy images and overly optimistic or overconfident for the hard images. And unfortunately, the second example on the right-hand side might still have marginal coverage, even though it's not really measured uncertainty in a reliable way. And so I think this point is actually often forgotten when people talk about conformal inference, but at least when beginners talk about conformal inference, but it should be kept in mind. And ideally, we would like to design conformal prediction methods that achieve conditional coverage, at least reasonably well in practice, even though it's difficult to prove in theory. So what can we do to try to make sure that we have reasonably good conditional coverage? Well, the first thing to do is to try to use a good machine learning model before applying conformal prediction. And there are some works that study basically how conformal prediction will give optimal prediction intervals that have valid conditional coverage in some imaginary asymptotic limit, as long as the model, the machine learning model that is being used underneath, is estimated a true distribution of y given x consistently. Unfortunately, however, in practice, deep neural networks and other complicated machine learning models do not estimate probabilities very accurately. In fact, they tend to be overconfident. So here I am showing the estimated probabilities for the top two labels computed by a convolutional neural network trained on the standard image classification dataset, in which I made some tweaks by making some images really hard to classify. And so you see that on the left-hand side, the neural network model is estimating that the ship is 96%, it's 96% probability of being a ship, which is good. But on the right-hand side, the machine learning model is telling me that this image is 99% confident. It's 99% likely to be a deer. And that to me looks a little bit overconfident. In fact, the image was a dog before I removed most of it. So the problem is that if you start with a machine learning model that is this overconfident, conformal inference can get you marginal coverage, but it will not give you anything that resembles conditional coverage. And so we would like to use machine learning models that are not overly overconfident. And there's a long history in the machine learning literature of developing techniques to try to mitigate overfitting or overconfidence. And the one that I want to talk about today is early stopping. So early stopping refers to, specifically in the context of neural networks, neural networks are trained by taking stochastic gradient steps for a large number of iterations. And early stopping basically consists of stopping this learning process, not when the loss function on the training data is minimized, but when the loss function on some holdout data set that is not used to calculate the gradients is minimized. And so we call that the validation set. And so the idea is that this approach avoids overfitting, and that often also mitigates overconfidence. So the idea of using conformal inference to construct prediction sets starting from a machine learning model that was trained using early stopping is not new. Several papers have done that. But the standard way they do it is that they use two separate data sets. One for, well, they use three data sets. So they take the data set and they split it in three parts. The first part is used to calculate the gradients to train the deep neural network. The second data set is utilized to determine the early stopping rule. So it's used to monitor the performance of the model while training, and it's used to decide when to stop in order to obtain a model that is not too overfit. And then the third data set is used to calculate some residuals that will be used to calculate the conformal prediction sets. And it's important that these three data sets are kept separated, at least in theory. And that's what prior works that I'm aware of did. So the reason why it's important to keep the early stopping and the residuals data sets separate, at least in theory, is that conformal inference requires the test point to be exchangeable with the data used to calculate the residuals, conditional on the model that we trained. And so if the early stopping data affects the way that we train the model, and it affects it because it determines when we stop, then that data set is no longer exchangeable with the test point once we've selected the model. And so in order to avoid that, we use a third data set to calculate the conformal inference residuals. And this is what allows conformal inference to achieve a provably valid marginal coverage. Now, the question of this talk is this really necessary? Because it seems a little bit wasteful that we have to split the available data set, which may be valuable, into 3 separate parts, only one of which can be used to really train the model by evaluating the gradient. So one approach that allows us to obtain a conformal inference without any kind of data splitting is a classical approach known as full conformal prediction. So here the test point is actually used to train the model and also to decide when to stop. And the fact that the test point is used in an exchangeable way with the labeled data means that we don't have to do any data splitting. Now, unfortunately, this means this kind of approach is not very practical in general, because using the test point for training means that if you want to deploy this model for different test points, you have to retrain every time. And so it can be quite expensive, but it does achieve probably valid marginal coverage. So another alternative approach, if we don't want to do too much data splitting, would be to simply close our eyes and double dip into the validation set used for early stopping. Now, what I mean by that is that you split the data in 2 parts, one for training and one for early stopping, as people in machine learning typically do when they talk about early stopping. But then after you have you train the model and you decide when to stop, you apply conformal inference using the same validation data used for early stopping. Now, I said earlier that this is not theoretically valid, but a practitioner may want to try to do that anyway. So this doesn't work too badly in practice. In fact, it works quite well. But in theory, it doesn't actually work all that well. So there is one work that basically developed a lower bound for how this type of approach can work. And this lower bound is obtained through the DKW inequality. And it basically tells us that if we do this, the coverage of the conformal prediction sets will be smaller than 1 minus alpha by a factor that scales as basically square root log t, where t is the number of models that the early stopping algorithm can pick from, divided by square root n, where this n is the number of data points in the validation set. And this type of scaling doesn't seem to be too bad. It does go to 0 as the size of the calibration set increases, and it doesn't grow too fast as the number of gradient steps increases. But unfortunately, if you evaluate this in practice, it tends to be pretty big. And there's also other bounds that you can obtain. So in this paper, for example, we obtained a different bound that depends on the cumulative distribution of the beta distribution. It's a little bit hard to read, but the idea is that if you work out the algebra here, this bound will scale similarly to the DKW bound, but it often has a smaller constants. And if you can also combine these 2 bounds to get a hybrid bound, but the story remains that this is quite conservative in practice. So for example, if you're aiming for 90% coverage, this bound basically tells you that by double dipping, you will basically, so 90% coverage is here. So if you are aiming for 90% coverage, you will basically find about 82% coverage. And so that's a pretty big drop, which we can understand by looking at what is the alpha value that you should use in order to achieve the coverage that you would want. So if we want 90% coverage, so in theory, we would want a 10% alpha level, then even the best one of these 2 bounds tells us that we should use alpha 0.05 in the conformal inference algorithm. And this happens to make a pretty big difference in practice. So here is some experiment using real data, and this naive double dipping approach with the theoretical correction, basically by changing the alpha level using the plots that we saw before, gives you very large prediction intervals. So here I'm showing the size of these prediction intervals. We guarantee the 90% marginal coverage. And the light blue curve corresponds to this naive double dipping approach with the theoretical correction. And you see that it's too conservative in practice. It gives us marginal coverage close to 100% instead of 90. And the prediction sets are very large compared to what you get with data splitting. I will come back to this approach, to this plot later in more detail, but the idea is that we can also compare here the data splitting approaches. So this splits the data into 3 parts and is theoretically valid, with the full training approach. So full training gives you smaller prediction sets. So full training means we don't do any early stopping at all. But the conditional coverage, which is something that we can measure empirically, is very low. So this is something that people often miss when they look at conformal prediction sets and they say, oh, we obtain smaller prediction sets. Yes, but at what cost? Sometimes the cost is that you don't actually have the individual level conditional coverage that you would like to have. You just have some kind of average coverage, but you're not quantifying uncertainty precisely in a reliable way. And so that's what having low conditional coverage means. So ideally, even though we cannot prove in theory, we would also like to have high conditional coverage. And you see, full training is not doing that, which is why early stopping is useful. Unfortunately, if you want to do double dipping and you get kind of the best of both worlds, you lose a lot of efficiency because you need to do that theoretical correction. And so the method that we present in this work is called conformalized early stopping. And what conformalized early stopping does is that it uses early stopping without an additional data split. So basically it only has 2 data splits, one for training and one for conformal inference and early stopping. But it's theoretically valid. And that means it has guaranteed marginal coverage. And so it enjoys the benefits of early stopping in terms of achieving high conditional coverage and small width, but it also works well in theory without any additional correction. And as we will see, the price you pay here is that it's more computationally expensive, but it's not unreasonably expensive like full conformal inference. And so we're able to find this trade-off where we do a little extra calculations, but we get better performance in practice and rigorous theory. So now, in the time that is left, I will try to give you a very quick overview of how we can achieve this. So the key idea is that we use the test point to select the model in the early stopping rule, but not to train the models. And so in this sense, it's a little bit of a hybrid between the split conformal inference approach and the full conformal inference approach. So we take the label data, we split it in half, or in two subsets. The training data set is used to evaluate the gradients and to train the machine learning model. And what we do is that we train this neural network for a large number of epochs or gradient steps. And at regular intervals, we store the candidate model. Okay, so this will require some memory, and so that's where the computational cost partly comes from. But it only has to be done once, and unless you have a giant neural network, it's not too expensive to do this. Then, using the calibration data, the holdout data, and the test point that we mix together, we select the best model using this holdout loss. And the key point here is that the test point is involved in this model selection, okay, as if it were a validation point itself. Now, in order to do that, you need to give a label to the test point, and we will give it a dummy label. So if we're working with classification, we will repeat this procedure for every possible dummy label that the test point might have. And so for every possible dummy label of the test point, which in classification is a discrete quantity, it may not be very large, we obtain a different early stop model. And then somehow we can combine those predictions and obtain conformal inferences that have guaranteed marginal coverage. So here's the procedure. I will come back to it if there are questions, but it follows the general idea, and we can prove that this procedure has valid marginal coverage, while in practice it enjoys the advantages of early stopping. And so here's another example where we show that basically this leads to smaller prediction sets, and in fact the conditional coverage here is not shown explicitly, but it will be very similar to that of that you obtain with early stopping. So this kind of procedure basically works like early stopping, but it has the guaranteed marginal coverage, and it overfits less compared to full training, so it will give you higher conditional coverage and sometimes even smaller prediction sets compared to full training. Now, what's a little more interesting is how can you do this for regression? Because the key idea for classification was that we had to repeat the early stopping rule for every possible value of the dummy label of the test point, which is clearly not feasible for regression because the label there can take infinitely many values. So this can be solved by looking a little more carefully at what is the early stopping model. So the model that we select with early stopping is basically the model that minimizes the loss function, the cumulative loss function, calculated on the holdout dataset. In our approach, the holdout dataset also involves the test point, xn+1, with the dummy label y. So this on the left-hand side is the model that we select for the test point for any particular value of the dummy label y. And if you're doing regression and you're using the squared error loss, then we can write explicitly what this loss function is. And by looking at this, you will see that the function that we're trying to minimize is quadratic in the dummy label y. And the problem was basically solving this optimization problem for every possible value of y is basically equivalent to the problem of finding the lower envelope of a set of t parabolas with different parameters, where capital T is the number of gradient steps or the number of candidate models that we want to pick from.
Hi,
So-
Professor.
Yes.
You have 5 minutes left.
Okay, thank you. And this turns out to be a pretty classical problem. In our special case, because these parabolas have all the same shape, because you see that the shape here comes from this quadratic term, and it's the same for every possible model T, then they're just shifted. So it turns out that these lower envelope has capital T knots. Okay, so it has capital T knots, and they can be found efficiently with a divide and conquer algorithm at computational cost T log T. So basically, that's the sort of cost, this cost of sorting. So after you find this lower envelope, you can basically write the optimal early stopping model as a step function with order T steps. Okay, so in fact, you can show that it's typically exactly equal to T. And once you write this as the step function with no steps, you can come up with this algorithm. So let's define BL as the interval between two particular knots of this step function. And so what we need, basically what we can do is that we can transform this regression problem into a classification problem where the label is basically the interval in which the value of y might be. And we have a capital T possible intervals of this type. And so what you do is that you go and pick the optimal model for each of these intervals, and we know that there's only one optimal model for each of these intervals. So we don't have infinitely many selected models, we just have capital T of them. And then you calculate the residuals for each of these intervals, and you basically apply conformal prediction. So conformal prediction will give you a prediction interval for each of these possible intervals. And then you go and intersect the conformal prediction intervals that we constructed with the interval between the two knots that we were starting from. So that way we can make them smaller. And then we take their union. And if there are any gaps in the union, we fill them, just so that in the end we have a prediction interval. So this complicated expression here is basically saying that is basically giving us an interval in the end. And this interval will not actually be very large. And why? It's because most of these prediction intervals, as a function of the bucket in which we are, BL, will actually be very close to each other. And so we're taking the union of some intervals that largely overlap with one another. And so most of the time, this will basically just be one conformal prediction interval calculated with the typical optimal model that doesn't change much. And so this interval is usually not large, and it is guaranteed to have valid marginal coverage. Okay, so we can prove theoretically that this procedure will give a prediction interval with marginal coverage. If you don't like using a squared error loss, you can also extend this idea to work with quantile regression. And so in this case, the machine learning model is estimating 2 quantiles. There are techniques like this conformalized quantile regression for transforming this model into a prediction interval with valid coverage. And here we can basically obtain the same property, but using early stopping to decide when to stop the model that does the quantile regression. The only difference is that we will look for the lower envelope of a set of piecewise functions with this V shape instead of parabolas. But you can see that basically the problem is equivalent to that of parabolas, and we can still solve it in t log t time. So the conclusions is that this conformalized early stopping procedure achieves good performance because it can take advantage of a model trained with early stopping that is less overconfident. It often works very similarly to the heuristic double dipping procedure, which kind of suggests that conformal inference is pretty safe after early stopping without the need to do any theoretical guarantees. But if you want to have, without the need to do any theoretical corrections using DKW or Markov inequalities. But if you want to have precise theoretical guarantees, conformalized early stopping gives them to you. And what's also nice about this is that even though I talked about deep neural networks and early stopping, the same idea can actually be used to tune any other type of machine learning hyperparameters. So if you're interested in tuning the sparsity parameter of the lasso instead of the early stopping parameter of a deep neural network, you can basically do the same thing in that case. And we have some software online if you want to see how this is implemented and how it works in practice. This was developed by my students, so I'm grateful for them for putting them online. I'd like to thank you for your attention. I'd be happy to answer any questions.
Thank you, Professor Cecilia, for the wonderful talk. I have a question in one of your slides with 3 figures. Could you go back to?
Was it this one maybe?
Yes, this one.
Yes.
So the full training has low conditional coverage, but it achieves the correct marginal coverage.
Yes.
Could you explain?
Oh, that's because, so conformal inference, if you apply correctly, always gives you marginal coverage, regardless of how bad the machine learning model that you begin with is. That's the whole appeal of conformal inference. Full training, in this case, gives you a very overfitted model. And so conformal inference can still fix it. And the price you pay for that, though, is that it will not have good conditional coverage. That doesn't always happen. Sometimes full training leads to very large prediction sets, as we saw in this example. Okay, so here, full training could give you very large prediction sets, but very often, what it does is that it gives you low conditional coverage, and you can understand it by looking at this example. Deep neural networks in particular, what they do when they overfit is that they become overconfident. And if you start from this kind of model and conformalize it, what you get are the prediction intervals not on the left, but those on the right.
Thank you for your answers.
Matteo, there is one more question. If you can look at, could you can see the question, right?
I can see it. Oh, okay. So
the last one.
Could you explain again how this proposed conformalized early stopping method helps with the problem of over-under-confidence? Okay. So what we want, so the purpose of early stopping is to try to mitigate overconfidence. If you stop here, instead of continuing training for a large number of iterations, you mitigate this overconfidence approach. So here I don't have the example, but these estimated probabilities, they will not be, for the hard image, they will not be as extreme if you train with early stopping. Okay, so this example here was trained with a long number of iterations. Usually, if you train with early stopping, it's not that bad. And so if it's not that bad, you will obtain conformal prediction sets that look a little more like these on the left than those on the right. But without conformalized early stopping, if you want to use the benchmark standard procedures, the price you pay for using early stopping is that you need an additional data spread. And so now if you're training a model using fewer training data points, you're losing something. You may be losing something in terms of conditional coverage, or you may lose something in terms of size of the prediction intervals, which is what we're seeing excuse me, what you're seeing in this example. With data splitting, you get much higher conditional coverage compared to full training, but it's not as good as what you get with conformalized early stopping, because with conformalized early stopping, you have a larger training sample, so you learn a better model.
Thank you.
Thank you, Matthew, for your answers. Due to time limits, we need to save additional questions to the end and move on to our next speaker. Thanks, Matthew, again. And
Okay, thank you.
if you have any, for audience, if you have any questions for the previous speakers, please also feel free to submit in the Q&A. You will have a second chance to ask those questions. And our last speaker, Professor Lee Harley, is from Stanford University. He will talk about conformal risk control. Professor Lee mainly works at the intersection of econometrics and statistics. A large portion of his research focuses on empowering statistical reasoning with machine learning and augmenting machine learning with statistical reasoning. Professor Lee, it's all yours now.
Thanks for the kind introduction. Can you hear me?
Yes.
Yes.
Great. First, I would like to thank the organizers for inviting me, and this is my great pleasure to share what I did in the past 2 years on conformal prediction. And this talk is going to be like a tutorial on conformal risk control. And this talk will feature joint works with all these amazing collaborators: Anastasio, Stephen, Emmanuel, Mike, Jitendra, Adam, and Tal. So thanks to the previous 3 speakers who have already set up the stage for conformal prediction. And here, just to fix the notation, we know that conformal prediction is to generate prediction sets that cover a certain fraction of future points. And in this talk, we will use xi, yi to denote the data, where xi is the covariate and yi is the outcome. So here we assume that xi has this domain curly x and yi has this domain curly y. And we also have this future data whose x has already been observed, but yn plus 1 has yet to be observed. So then a prediction set is simply a mapping from the domain of x to 2 to the y. And here lambda is just a cutoff for nonconformity scores. And here the domain 2 to the y is quite important. Because, for example, if you have a continuous outcome, then we want to generate intervals. So interval is just in the 2 to the y. Or if you have discrete outcomes, like labels, then you want to generate a set of labels. So then conformal is going to find this lambda hat, or find a cutoff for the nonconformity scores, such that if you apply this interval onto the future data point, it will achieve at most alpha miscoverage on average. So this guarantee is very strong in the sense that it holds infinite samples and works for any predictive model and any distribution as long as the data are IID or exchangeable. However, there are 2 limitations. One is that this action space or prediction space 2 to the y can be uninterpretable when your outcome is high dimensional. And on the other hand, here we can rewrite this miscoverage as an expected loss function, where this loss is a binary loss for intervals. However, as I will show you in the next few slides, this 0-1 loss might be too restrictive or brittle. And here's the example. So let's say we have these medical images, and our goal is to detect tumor pixels. So in this problem, the covariate is this image, which is a d by 3 tensor. And the outcome is no longer a single number, but rather it is a subset of this d by d pixels. So if we were to generate prediction intervals or prediction sets, then that's going to be lie in this 2 to the y space. And that means we're going to generate a set of subsets of the pixels. And that thing is super hard to visualize or interpret. And then we can adapt conformal inference a little bit by reducing the action space from 2 to the y to y, meaning that now we are not giving you a prediction set, but rather we just give you a point prediction, which is another subset of pixels. But here we can consider the same loss function or a similar loss function by asking whether the true set of tumor pixels are completely included in the predicted ones. So again, this is a binary loss, which is analogous to the binary loss used for conformal prediction. And here are the results. So you can see here, the black pixels are true negatives and white ones are true positives. So they're good. However, these blue ones are false positives. And we see that in each of the images, we have a lot of false positives. So that's not surprising. That's not because this method doesn't do a good job. It's simply because the loss function here is too brittle. Because this loss function is asking for fully cover all the tumor pixels. So instead, we would argue that if we change the loss function to something like a false negative rate, which is defined as the ratio of two things, where the numerator is the number of tumor pixels which are not detected, and the denominator is simply the number of tumor pixels. So we would argue that if false negative rate is low, then the prediction is good enough. So we don't need to include all the pixels. It's good enough to include, say, 95% of pixels. So turns out if we apply our method called conformal risk control, then we can reduce the false positive and false negative dramatically. So that means we need to care about both the action space and loss function. Then going back to our notation, again, we will assume that we have data, future data, and predictions. And here, we allow the predictions to be a mapping from X to any other space, Y prime. And here, Y prime could be Y, or 2 to the Y, or something else. Say, you take part of the Y and take and consider point prediction. And then for the rest of them, you consider prediction set. So here, we don't want to impose any restriction on this curly Y prime. And on top of this structure, we need to define a loss function, which is a function of Y and predicted Y. And then our goal becomes to use this lambda, using our data to find this lambda hat, such that if you apply this, or if you deploy this rule on the future data set, then the expected loss function will be upper bounded by alpha, by a target level. So again, this method will inherit all the advantages of conformal prediction, but on top of that, it can also allow for arbitrary action space and general loss functions. So to illustrate how our method works, let me revisit conformal prediction. And then specifically, I'll give one instantiation called conformalized quantile regression. And here, I'm going to use an equivalent formulation of CQR, which might be slightly different from what you have in the literature. But this formulation is super useful to motivate our procedure. So let's say we have this data, and then we use some external data to estimate these two quantiles, upper one and lower one. And then we begin to inflate it a little bit by lambda. So here, we will use this lambda to measure the inflation. And then for each lambda, we will denote T lambda X as the set or as the interval given by the low quantile minus lambda and the high quantile plus lambda. And on the right, you can see here, there's a knob, which is on the scale of lambda. And at the moment, lambda is very small. And for each lambda, we will try to estimate the miscoverage, which is roughly the average miscoverage on the calibration set. But here we need a small adjustment, which is to add 1 onto both the numerator and denominator. And here, this yellow dots just give this miscoverage estimate. And then let's turn the knob to the right. And this will trace the whole curve. And then we will find the crossing point between the target line and this yellow line, and call that lambda hat. And this turns out to be equivalent to conformal prediction, or at least split conformal prediction. And then we can show that the probability of, or the miscoverage rate will be below alpha. So a natural extension of this procedure is to replace everything to another loss function. And here, going back to this medical image example, we will define T lambda X as the set of pixels such that certain score is above 1 minus lambda. So here the score can be obtained by training a neural net. And then we can take the softmax score as the score, which essentially predicts the probability of each pixel being a tumor. So here we take 1 minus lambda because we want this set to be monotonally increasing in lambda. So it's not essential. And again, we're turning this knob. And here, instead of estimating the miscoverage, let's try to estimate the false negative rate. And everything is exactly the same, except that now I replace this indicator by this instance-wise false negative rate. And again, we turn this knob until we find the first point that hits this target level. And we take that as lambda hat. Then we can show that the expected false negative rate will be below alpha. So that's a specific example with FNR being the risk function and this set being the prediction set. And here's the general theory. Again, this is just a set of notation I introduced before. And a crucial thing is now we can reduce or compress all of this into one quantity, that is the individual loss function, which is defined as the loss evaluated at ice point and tuning parameter lambda. So this turns out to be a random function. And then our main result is that suppose this individual loss functions are IID, non-increasing and right continuous functions in lambda, such that they're bounded. Second, the minimal value is less than or equal to alpha, so that this risk control can be achieved. Then we can define lambda hat to be the infimum of lambda such that this estimated risk is below alpha, where this estimated risk is defined analogously to the miscoverage or estimated false negative rate, which is roughly the average loss function on the calibration set, but subject to some slight modification. Then under all these conditions, we can show that the risk is controlled at level alpha. Then just a couple of comments around this result. So first, it turns out the split conformal prediction is a special case where we set this loss function to be a binary loss, and this prediction set to be the set given by thresholding the nonconformity score. And then if this expected loss is continuous in lambda, we can show that we not only achieve the risk control, but also we achieve that in a tight way, in the sense that this expected risk will be lower bounded by alpha minus 2b over n plus 1. And for conformal, or in general for binary loss, we can improve this to alpha minus b over n plus 1. But in general, we show that this factor of 2 is tight. It cannot be improved. And more general, if we consider non-monotonic loss function, turns out we have this impossibility result showing that for any epsilon, we can find a non-monotonic loss function such that this program will give you a risk close to B, close to the upper bound. So it's not informative at all. But on the other hand, if we are willing to assume some regularity conditions on the expected risk, and if we're willing to take asymptotics, then we can show that this lambda hat will give you asymptotic risk control. But in general, this is not something we want. So I would say this is more like a sanity check, showing that this lambda hat can be well behaved. But in general, we do want finite sample control. So then we propose monotonizing this estimated risk, which can give us finite sample control again. However, it is in general conservative. And in our paper, we discussed quite a few applications, including FNR control in tumor segmentation, a multi-label classification. And we also talk about how to control graph distance in hierarchical image classification and F1 score control in some natural language processing tasks. And here, I'm not going to talk about that. So far, so good. It seems like we already extend conformal prediction to general risk control. However, in some cases, that's not enough. So one concern about conformal prediction, as Mateo mentioned in his talk, is the lack of conditional validity. So one way to illustrate this is that conformal prediction achieves this average control, which can be rewritten in this way, where we first take the coverage or miscoverage with respect to the future point, and then we take the average across our training set or calibration set. So suppose our target level is 90%, then that means if we have a lot of analysts, each of whom has access to one data set, then on average, or average analyst can achieve 90% coverage. However, it could be that 50% of them gets 80% coverage, and the other 50 get 100% coverage. So in some cases, we may want to control the fraction of analysts whose coverage is below 90%. So this motivates another criterion called tolerance region, which is requiring that this conditional miscoverage is below alpha with probability 1 minus delta. So it turns out this is a classical concept in statistics, which can be dated back to the 1941 for parametric models. And then there was a very influential paper by Vovk in 2012 generalizing this idea to conformal prediction. So he proposed this conformal tolerance region. And in a recent paper with Stephen, Emmanuel, Yaniv, and Motel, we also generalized that to simultaneous confidence band. And in machine learning literature, this is called a pack guarantee. So here it turns out the conformal tolerance region has exactly the same structure as the conformal prediction. So again, going back to CQR, remember that we have this knob, we have this CQR score. And before we estimate the miscoverage by this yellow dot, but here, in order to generate conformal tolerance region, we're going to generate a pointwise upper confidence bound using the Klopper-Pearson confidence interval for binary proportions. And that will give us a red point. And then we turn this knob and we stop until the first time this red curve hits the target level. And we call that lambda hat. And then we can show that this lambda hat can give us the pack control. So similarly, we can use the same idea for FNR control in this tumor segmentation example. It's just that now our loss function is no longer binary, so it's not a binary proportion problem. But instead, we can use some tools developed recently by Watman Smith and Ramdas, which turns out to be much tighter than Hofding. And we can use this to construct a pointwise confidence interval. And we turn the knob until the first time this red curve hits the target level. And again, we can show that this lambda hat can give us the pack FNR control. So in general, we have the following theorem, which looks very similar to the first part. That is, we can set lambda hats to be the infimum of lambda such that this upper confidence bound is below alpha. Then we can achieve the pack control. So again, the split conformal tolerance region is a special case with this binary loss. And for bounded loss, we are using this Watt-by-Smith-Ramdas bound to get this upper confidence bound, and turns out to be much tighter than other concentration inequalities in the literature. And a very important point here is that there's no need to compute simultaneous upper confidence bound on the expected risk. We just need to get a pointwise confidence bound. Because if you talk with a machine learning theorist, then usually the solution would be to apply empirical process theory to get a simultaneous confidence bands for this risk curve. However, if you really apply those concentration inequalities in practice, then they're going to be very conservative unless your sample size is like 10 to the 6 or 10 to the 7. And I guess Matteo also showed some of that in his talk, where if you apply those tight concentration qualities, you still get a very loose result because they're only tight in rates. They're not very tight in constants. But here we just need a pointwise upper confidence bound. So that's quite important. Okay, so that's pretty much about monotonic risk. And for monotonic risk, we have already shown how to achieve expectation control as conformal prediction. We also show how to achieve the pack control as for conformal tolerance region. But a natural question would be how we can handle non-monotonic risk. So in this case, one simple example is going back to this tumor segmentation example. Instead of controlling false negative rate, we can control the false positive rate. which is defined as the expectation of this ratio where the numerator is the number of detected pixels which are not tumors, and denominator is the number of detected pixels. So here, because both the numerator and denominator involves lambda, so there's no guarantee that this is monotonic. But still, we may want to ask for a lambda hat such that this lambda hat can give us pack FDR control. So here, just to illustrate what's happening, again, we can estimate the MISS or estimate FDR using the calibration set. And this will give us this yellow curve, which is non-monotonic. So then can we use the pointwise upper confidence bound and do the same thing as before? Turns out this is not valid because we lose the monotonicity. But another question is, can we use the uniform upper confidence bound using the empirical process theory? However, so although this is valid, but as I mentioned before, this turns out to be very conservative. So what we found here is another way to look at this problem through the lens of multiple testing. So what we're going to do is we first discretize lambda. And for each lambda, we estimate FDRs simply by this average. And then for each lambda, we consider a statistical null hypothesis that the true FDR at this lambda is above alpha, meaning that this alpha cannot control the FDR.
Professor, you have 5 minutes left.
Yeah, thanks. And then we compute a marginal p-value for this hypothesis. And here we give the curve of the p-values. And our key result for London test procedure is that if we can control the family-wise error rate for this multiple testing problems, then we can choose any representative from the rejection set and control and achieve the risk control. So here, family-wise error rate is a very important concept in multiple testing, and I don't have time to dig into that. But a very common approach to achieve FWER control is Bonferroni correction, meaning that we split our budget. We normalize our budget by the number of hypotheses here, and then we reject every p-value that is below delta divided by n lambda. So although this approach is valid, but it's too conservative, mainly for 2 reasons. One is that it doesn't show any adaptivity to the FDR function, because here, although we have a multiple testing problem, but this multiple hypotheses are highly correlated, and they're corresponding to this risk curve. So we should expect this curve to be very smooth and nearly monotone. And another reason is that this adjustment depends on the number of discretization points. And then this will give the user a bad incentive to gain the number of points they choose. So instead, we are suggesting using another procedure called fixed sequence procedure, which can date back to the 1980s. And this procedure will proceed in the following way. So it would not do any multiplicity correction. And what it does is to start from the first hypothesis and see if this p-value is below delta. And if it doesn't, then it will move to the right. And it will keep doing so until the first time there's a p-value above lambda, sorry, above delta. Then it will stop and reject everything before. So it turns out this rejection set will control family-wise error rate. So at first glance, it may seem to be too good to be true because this doesn't involve any multiplicity correction. However, this is not strictly dominating Bonferroni because if you are very unlucky to have a large p-value at the beginning of the list, then you basically early stop and you never have a chance to look at the later p-values. So in general, this might not be a good procedure. However, in this problem, because we expect FDR curve to be smooth and nearly monotone, so this is still a good procedure. And also because it doesn't involve any multiplicity correction, so we don't need to worry about how many discretization points we start with. And then we will take the largest one as the lambda hat, and we can show that this will give us the risk control. And turns out we have many more general approaches called fallback procedure graphical approach, which were developed mostly in medical statistics. And it is a mature topic with over 30 years of history. And here, sorry, I don't know why this doesn't show up, but we have other applications in object detection, protein structure prediction, among others. So if you're interested, you can take a look. And also we have a lot of extensions. And for example, we can handle multidimensional calibration parameter lambda. We can handle multiple risks, distribution shift, quantile risk control, and U risk. And just to summarize, here we talk about two types of controls. One is expectation control, the other is high probability control or PAC control. And for conformal prediction, we have both, but they're restricted to coverage as the risk function and also prediction sets as the action space. And here in our work, we first generalize that to monotonic loss and any action space. And then we also think about how to handle non-monotonic loss. And in particular, London test can achieve the PAC version of the control. However, how to achieve expectation control for non-monotonic loss is still an open question. And here, we know that we have some asymptotic theory from conformal risk control, but it's asymptotic. And here, we can also turn the high probability control to expectation control, but that's going to be conservative. And I think there's still a lot to do here. And with that, I'd like to thank you all for your attention.
Thank you, Professor Lei, for the wonderful presentation. And dear audience, if you have any question for Professor Lei or the previous speaker, please use the Q&A session. And at this moment, I hope the host could bring back all the speakers and our organizer Vladimir and James onto the screen to join me in thanking all the speakers.
I have a question for Alex. I didn't ask him immediately after his presentation. What is the optimality property of the martingale conformal? As far as stopping rule, will you have it as early as possible in some sense, better than other?
Can you repeat it again? Because I couldn't.
In the martingale conformal approach,
yeah,
the stopping when you obtain using it, is it optimal in some ways? Is it the shortest?
it isn't optimal, and it's been proved long before us, of course. You can find the proof in our book, but you can look at the actual optimality. Yeah, it is optimal.
Okay, thank you. There is one more question to Liao. Can you see it in Q&A?
Yes. So the question is, how does the tolerance region plus FDR compare with controlling exceedance of false discovery proportion? So that's a great question. So here, they are different because the FDR is first taking average of the future data point. And then the high probability part purely comes from the training set. But of course, we can also consider controlling the false discovery proportion with high probability. And that turns out to be a PAC version for quantile risk control, which has been discussed in another work. And it's not hard to generalize London test to that framework, because you can first find the equivalence between quantile risk control and expectation control, and then you turn that into FDB control.
Thank you. Are there any other questions? Maybe speakers want to ask questions.
Yeah, I do have a question for Professor Lei. I think it's very interesting. So you generalize the loss from the initial 0-1 loss to these other risks. So I'm wondering, when you solve the problem, like, do you consider the property of the loss function? Do they have to be convex in the parameter? And, for example, in your performance guarantee, do you use any property of the loss? themselves?
That's a great question. So for the second part, we assume that the loss functions are first monotonic, and second right continuous, and third bounded. So turns out monotonicity is very crucial because we show that there are counterexamples when it comes to non-monotonic risks. And right continuity is more like a regularity condition. And the boundedness is just to get a valid p-value, pointwise p-value. But if you don't have a bounded risk, then you could either turn to quantile risk control, which doesn't require boundedness, or you can construct asymptotically valid p-values using central limit theorem. So I would say monotonicity is the most crucial one. But for London test, if we are willing to use multiple testing or family-wise error rate control algorithms, then we don't even need to assume monotonicity. So basically there we can handle any risks. It's just that when things are not monotonic, then the power could be low.
I see. Yes, thank you.
Thanks for the question.
Thank you.
There is a general question from chat. Let me read it. I'm trying to better understand the difference between marginal and conditional coverage. How do marginal and conditional coverage relate when considering predictions for a set of new examples? What type of information does each type of coverage tell us? Please feel free to unmute yourself if you would like to take this question.
I think Matteo is ready to answer, right?
Yes, okay, so I think maybe there was some confusion because we used the term conditional coverage to refer to different things. For example, between my talk and Eva's talk, and also it has also been used to, I mean, you can also condition yet other things that we didn't talk about. So marginal means basically that the prediction sets have coverage on average when you repeat the experiment, starting from the collection of the calibration data and including also the observation of the test point. That's what marginal means. So that basically everything is random. Then conditional means that you want to have coverage condition on something else. So you could condition, for example, on the calibration data, which is what Professor Lei was talking about, or that it's not mutually exclusive, or you could condition on the test point that you have observed, which is what I was talking about. You can also condition on other things. So what is the reason for conditioning on the calibration set? Well, that's if you want to make sure that you have valid coverage on average over multiple test points in one particular study, which is what Professor Lei was talking about. The reason for conditioning on the specific test point makes sense. For example, if you expect to have heterogeneous data, you have some test points that are difficult to predict and some test points that are easy to predict. In that case, it's not enough to have valid coverage on average over both types of prediction sets. That kind of defies the whole point of doing uncertainty estimation, in my opinion, because you wouldn't like the idea is that you want to have prediction sets that are large when you don't know, and they're small when you know, for sure. And so in order to do that, basically you need to make sure that they're valid conditional on the difficulty of the test point. And the difficulty of the test point is captured by some features of the test point. So by conditioning on all possible features, you can also cover, you will cover that. It's not necessary, and in fact, it's difficult to condition on every possible feature. But if you could do it, then you would basically know that you quantify uncertainty both for the easy cases and the difficult cases in a sort of adaptive way.
Thank you, Matteo, for the detailed answer.
Alex, if I may, quick question. In your wine example, you showed this convincing plots of the martingales for the, I'm talking about wine example. But if you plot the error rate or error rate of your prediction, and then at some point the error rate will be going up, right? Because you're predicting the data with different distribution. How long will it take? Will it take longer than looking at the marketing?
Are you talking about assessing error rate but without changing point, or am I missing something?
Right. Just looking at how the error rate changes.
But in fact, you can do it, of course, by applying this classical approach like Shiryaev, Roberts, and the rest. But the problem, of course, in order to find this change point, you need to know what the distribution was, and before the change point and after. But I don't know how much difference and how many more mistakes you can make it. Another problem is, of course, I haven't mentioned this, but there is a delay between change point and when we started to get this change point. And I showed you that it's actually when you use different procedure like Willi and Shiryaev, Roberts, and Kusam, they all have a sort of different delay for median mean absolute deviation. But again, the number of mistakes, I don't know the answer on the classical stuff. I can find out what's in our approach. But it's again, I showed in one of the slides as in absolute deviation, it was not 0.45 for the when you train on the white wines and apply to the same white wines, and considerably worse when you apply to a different distribution in setting as a regression problem, of course.
Thank you very much. We are over time, but we can continue this interesting discussion for much longer. On behalf of organizers, I want to thank all our speakers for the wonderful presentations and all participants for their interest and their questions. At this point, we are closing the webinar, and we all wish you the best. Thank you.
Thank you.
Thank you, everyone.
Thank you.
Thank you, everyone.
Thank you.
Bye.